If we want to understand the reactivity of a carbonyl, we need to look at what the resonance forms of a carbonyl look like to determine where the electron density is. Which part of the molecule is an electrophile, which part of the molecule is a nucleophile. And these resonance forms are the same for all carbonyls, regardless of which functional group it's in. So we can push that pair of electrons out, and there's a resonance structure then that we can draw that has a positive charge on carbon and a negative charge on oxygen. If I look at the hybrid structure, I would say that there's a partial double bond here, there's a partial negative charge here, and there's a partial positive here. A lot of times we'll draw that without drawing the partial bond, and we'll just say that if we have a carbonyl, there's a delta minus on the oxygen, there's a delta plus on the carbon. Also, because it's got a pi bond, the hybridization of this carbon is sp2, which means that the shape is trigonal planar. And since it's trigonal planar and flat, that means this carbonyl, if I'm going to react it with something, which will be something like a nucleophile, it's very available to react with. Because it's sp2 hybridized and trigonal planar and flat, there's very little steric hindrance to reactions at this carbon, unlike what we saw in Chapter 7 with nucleophilic substitution reactions, in particular with SN2 reactions, where sterics were a big deal. So if we have something with a carbonyl on it, and we react it with a nucleophile, there are two general mechanisms that we're going to see. And it all comes back to what I was talking about in the last section, and that is whether or not we have a good leaving group. So we'll start with ones that have a poor leaving group. So these are ones with H or R, which means aldehydes or ketones. So I'll just give an example of an aldehyde. And if I react that with some kind of a generic nucleophile. As always, the question that you want to ask yourself is, who has electrons, who wants them? Who's your nucleophile and who's your electrophile? Well, in this case, I already told you what the nucleophile is. This is the nucleophile. So what part of the carbonyl is the electrophile? So who wants the electrons? The answer is the carbon, because there's a delta plus on carbon. There's a delta minus on oxygen. So if this nucleophile comes in, it will add to the place that wants electrons. However, we need to break a bond there, because if we just made that new bond to the nucleophile, we would have 5 bonds to that carbon. So the pi bond breaks and goes out onto oxygen. So at this point, what you need to ask is, do I have a good leaving group here or not? If I have a good leaving group, then this electron pair can come back down and reform the carbonyl, and that leaving group could leave. In this case, hydride is a very bad leaving group. Remember, it's the conjugate base of an extremely weak acid, H2. It has a pKa of about 35. So that doesn't want to leave. So if I don't have a good leaving group, the only thing I can really do is then react that with something else to get rid of my charge. Typically then what we do is we'll react with water, and our alkoxide that we have here gets reprotonated by the proton off of water. So now we have to try to think about what kind of a mechanism this is. So here we added a nucleophile, and then we just reprotonated. So if we had to look at what type of reaction it is, whether it's an addition, elimination, substitution, or rearrangement, it's an addition. It's an addition of a nucleophile. So the reaction is a nucleophilic addition. And you can do the exact same thing with a ketone as we just did with an aldehyde. So let's look at another example. This time, let's look at an example that has a good leaving group bonded to our carbonyl group. So I just put Lg. An Lg could be an ester, could be OR, could be a carboxylate for an acid anhydride. So it could be OR minus, carboxylate minus, could be X minus for acid halides. Could be any of those things. And I react this now with a nucleophile. Once again, I would challenge you to pause the video and you try to draw what's going to happen when the nucleophile attacks this molecule. Same question, who has electrons, who wants them? Nucleophile has the electrons, the carbonyl wants them. We have to break the pi bond first. Pi bonds, of course, are weak and they're the easiest to break to make our intermediate. And now if you remember last time I was asking, do we have a good leaving group or not? And in this case now we do. So this electron pair can actually come back to reform the pi bond, and now our good leaving group can leave. to make our neutral molecule. And in doing so, we reform the carbonyl with the nucleophile on it, and then we have our leaving group minus. So if we want to name this mechanism, again we have to look at what happens. We reacted with a nucleophile. So we reacted with a nucleophile, but what happened? The nucleophile NUC came in and displaced the leaving group, so it's a nucleophilic substitution. However, we already have SN1 and SN2, nucleophilic substitution unimolecular and nucleophilic substitution bimolecular reactions, but this mechanism is different because it goes by an addition then an elimination. So first the nucleophile adds to the carbonyl, and then the electron pair comes back, eliminating the leaving group. So we have to have a different name for it to explain how it's a different mechanism. So what we call it is it's a nucleophilic acyl, and acyl is just another word for carbonyl. Nucleophilic acyl substitution.